Team presenting in this session is team number 7, RemoteHCS, also known as Doc in a Bag.
Same difference. Good to get this. Cool. All right. Okay. What are you doing? All right. Alrighty. Hello, everyone. My name is Nick. This is Charlie, Ryan, Joseph, and Ming, and we are RemoteHCS. So we have 2 advisors. The first is Professor Al Sheikh, and the second is Manish Ranjan, representing NanoHealth. So to get right into the problem we're dealing with, it is chronic diseases in India. So over 5 million people die every year from chronic diseases in India, and this is largely due to a lack of accessibility to healthcare. So there are only 0.7 physicians per 1,000 people in India, and many underserved communities have no access to basic healthcare at all. So our client, NanoHealth, in collaboration with Tabib, is trying to improve accessibility to basic healthcare in underserved communities in India. So by screening patients for hypertension and diabetes, they're helping at-risk patients get affordable healthcare. However, testing and data collection is currently done entirely by hand. So that is where we are coming in. So what we have created is a mobile diagnostic platform to automate the screening process. Our design uses digital medical devices interfaced with a Raspberry Pi hub to send test results to our Android application. Our easy-to-use Android application is a user interface that facilitates patient screening. It is connected directly to the cloud. This means it has access to a medical records database to automate storage and allow access to records from anywhere. By automating this process, we can reduce the chance of human error and increase efficiency while retaining a scalable, adaptable, and low-cost design. Overall, this will allow our client to reach more communities and more potential at-risk patients, increasing the impact they can have on chronic disease problem in India. So now we can take a look at the final design we have here. So starting from the top left, we have our device hub. Contained within is a Raspberry Pi microprocessor, a lithium-ion battery pack, and 2 printed circuit boards encased in a 3D printed plastic housing. So that is connected directly to our Android tablet, which is a new Tab G7, and then we have our 2 digital medical devices. So now Ming is going to talk a little bit more about our technical overview.
So to do our technical overview, we think it's best to show you a step-by-step use case of our project. First, the social worker is going to sign into our Android app. At this step, our REST API service is going to generate an authorization token to the user if the user is authorized. And next, the user is going to start by taking measurements of the patient using the medical devices, which is our glucometer and our blood pressure monitor, to get the biometric data. After that, after taking measurements, the devices will send the data to our Raspberry Pi hub via Bluetooth, and then the Raspberry Pi hub is going to forward the data to our Android application via Bluetooth. And the application will take in the data and fill in all the corresponding fields automatically and have it ready for the social worker to review. After the social worker review the data, they can send it in a JSON format via cellular network to our API endpoints on the cloud that's being hosted by AWS Elastic Beanstalk. And after the cloud service receives the request, our Django application is going to process the data and then write it into our OpenEMR database if the data is if the request is valid. And OpenEMR is the open source medical record management system that's been requested by our client. So to support all the functionalities, we have our 2 hosts on our domain name services. One is for OpenEMR and one is for Django application. For OpenEMR, if you see on the bottom part of the diagram, it's being hosted on an EC2 instance. It has a PHP front end and has a MySQL database. That's the main database it's supporting for all of our applications. And we did a lot of mapping and stuff like that to have the database to work with our Django application. If you look to the top of the diagram, it's our Elastic Beanstalk production environment. In the environment, there's an Elastic Load Balancer that would take in all the incoming traffic and distribute it to our two application instances evenly to maximize the performance of our application. And the app instances are in an auto-scaling group that would scale up and down depends on the demand of our system. Additionally, all of the components on the cloud are secured by network access control groups, and all the incoming traffic that's an HTTP to our elastic load balancer will be redirected to HTTPS to further our security. And next, Ryan's gonna talk about a Django application.
Hi, so I was in charge of creating the Django application. Django is a Python-based web framework that's very popular. And so we decided on using a RESTful API architecture to support interaction with our Android application. So probably the toughest thing that we had to deal with when creating the RESTful API, as Ming mentioned, we were dealing with a legacy database. OpenEMR has well over 70 tables, and we needed to know which tables were important, which tables had relevant information to the things that we were going to be discussing on the screening. So reading the data initially was not too bad, but inserting the data so that we could have OpenEMR interpret that data properly and then respond back on the clinical side of the application was actually very difficult. So also, Django is able to process all of these GET and POST requests. It restricts certain endpoints to certain POST or GET requests, and it also supports token authentication. I wrote some custom token middleware so that it will only allow the token to be valid for 2 days, and every time you sign in, it'll generate a new token, just for more security measures, and that way the tokens will expire. Additionally, Django is responsible for hosting our admin application. This is just a portal where admin users can go in to create and manage the lifecycle of users. We thought this is initially not part of our requirements, but we thought it would be very important and very prudent for somebody using the application to be able to easily create a user and then also easily deactivate them should they no longer be allowed to use the application. Additionally, it supports the browsable API, which we use for debugging purposes, and also being able to post and get data and test things out when the Android application was also under development. And next, Joseph will be talking about the Android application.
One of the main goals of our project was to allow users to remotely access records. This is going to be done through our application, which we built specifically for Android 5.1. The app will allow users to query the database, and depending on the results, they can either create a new record or choose one of the existing ones. If they choose an existing record, they're allowed to look at their previous medical history as well as any visits they may have had. When they're ready, they're able to begin a new visit and will be guided through an encounter with the patient. If the hub is available to be connected via Bluetooth, it will automatically connect when a new visit begins. If it's not available, however, the visit will be able to be completed by manually entering the test results, which you can see over on the right image. Once complete, they're able to review the visit and then upload it to the database. Any new patients will automatically be created, and any existing patients will automatically just have an visit created. And Nick.
So my job was to write software for the Raspberry Pi in the device hub. So it had to do two things. It had to retrieve the data from the actual medical devices, and then it had to send it over Bluetooth Low Energy to our Android tablet. So as far as managing the Bluetooth connection, I ran a Python RFCOM server script that set up the Raspberry Pi as an RFCOM server. And then it would listen for incoming connection requests from the Android tablet, and then accept that connection request and open up a Bluetooth stream over which we could push information. The second part of that was retrieving the data from the medical devices. So upon request from the Android tablet, I used Python retrieval modules, which would call C++ device drivers to grab the most recent result from the medical devices, format that appropriately, and then send it over Bluetooth to our Android tablet. So since the Raspberry Pi is going to be embedded in a casing, I had to automate this entire process. So I used a systemd unit service that would run on boot to initialize our RFCOM server. So now Charlie's going to talk about our hardware.
So in order to extract data out of the medical devices, they first need to be connected. So to connect the blood pressure meter, we used a USB cable, and to connect the glucose meter, we used a 2.5 millimeter auxiliary cable. And the printed circuit board had two main circuits that we're using. The first is a USB to UART converter. Because the Raspberry Pi, the pins we're using on the Raspberry Pi are the UART pins, so the data we need to get out from the medical devices need to be in, I guess, UART. So the first thing there is the USB UART conversion, and when the device driver is called, the data will pass through. The data will be converted and be readable on the Raspberry Pi. And the second circuit is a transceiver circuit. So the data coming off of the glucose meter is in RS-232. That gets converted into a UART. And readable by the Raspberry Pi. And all this is enclosed, again, in a case which also contains a battery, which has the ability to charge the Android tablet should it run out of battery. And next we have a video explaining our system. I guess, yeah. Here's
It's just also important to note that in this video, since we were limited to time, we just really want to show the interaction between somebody performing the test and somebody receiving the test, and a lot of it's just going to be taking place from the actual tablet itself. And then at the end of the video, you'll see what it looks like in the OpenEMR view of the same exact data that you had collected from the devices. Oh boy. Oh, yeah, sure. It's really good ass, I know. Oh no.
Oh boy.
Oh god.
Once more.
That's not us. Okay.
Oh my God.
What did you do? Where'd it go? Oh, there you go.
Earlier this week, we met with Professor Al Sheikh for our customer installation. He was very happy with their progress, and both of us, him and the rest of us, are really excited to continue improving on the work that we've done so far. Okay. And I think that's it.
Yeah, it's fine. All right, questions?
I don't know what happened, but like it got all like funky and weird.
I know.
So,
Yep.
what do we have?
Yeah, so these are specific ones. We actually chose these ones because there were open source libraries for us to use in creating the drivers. So, sorry.
Back here.
How much thought have you given to the overall security of your system, given that you're dealing with patient healthcare information?
We're applying multiple layers. So like first of all, it's API token authentication. So only authorized personnel can have access to our Android tablet. And then the communication between our Android tablet to our API application on the cloud, it's HTTPS. So like we forced it. All the HTTP will be directed to HTTPS. And then our database is hosted separately on the ECEDay instance. And then it's only we configured the network access control rule to only take requests from our elastic load balancer to the port 3304, which is what people usually use for SQL database. So we like put multiple layers and we try to secure the transaction as much as possible. Yeah.
Is the actual information itself encrypted though?
The database is not encrypted, but the communication is encrypted.
Okay, thank you.